Okay, how many of you people have been to the Smithsonian? The old Smithsonian building?
The red one.
The red one, built of red rock. Okay, this is the place that red rock came from. There's a quarry around the corner here. This is Chifley Mill Road, and this is the place where they cut the rock out of the quarry and shaped it into blocks to make the buildings. And you can see the blocks here. It turns out the best place to see the rock actually is in the ruins of this old mill building. The rock itself is a red sandstone, and if you see if I could find a piece of it somewhere, it's like I brought my hammer along.
Geologist with hammer.
Yeah, beware. Ah, yes. Close up on this, you're probably not even going to get it with a close up, but if I look at this very close up, I can see little sparkles in it, like glitter. Can you see the little tiny sparkles in there? That is glitter. It's mica. It's muscovite mica, which they mine and grind up and use for makeup. And the color of this is hematite color. This is a hematite cemented sandstone with a little bit of muscovite in it. And if you remember when I gave you the classification of sandstones, I said that arkose is a sandstone that's defined by having a large content of feldspar, but as a practical matter, usually just looking at it, you can't identify the feldspar. Instead, what you see is the mica, and that makes it 90% certain that it's going to have the feldspar in it too, so this is an arkose. So that's as far as the classification goes. Now, as far as the geology here goes, this particular rock was deposited in a structural valley that was produced when Pangaea, the old ancient supercontinent that was built 250 million years ago, started to break up again. When it started to break up and the Atlantic Ocean started to open up, you pulled apart the continent, and it was like pulling apart the two sides of an arch. The keystone in the arch, the top stone that holds it all together, then drops down. Well, the same thing happens when you pull apart the crust of the earth. Chunks of it drop down into structural valleys. Many of those valleys formed when it first started pulling apart. Today, you can see the same thing going on in western North America. Salt Lake City and Lake Tahoe are now about 60 miles farther apart than they used to be, because that whole stretch of land across all of Nevada and half of Utah is being stretched apart. The crust underneath is moving in two different directions. Now, if you'd like a good real estate tip, eventually that's going to open up and a new ocean is going to form there, just like the Red Sea is today, the two sides of the Arabian Shield are pulling apart. The best bet is that the line will go through Elko, Nevada. And you can get land in Elko, Nevada dirt cheap today. It's boiling hot in the summer, bitter cold in the winter, very dry. The land is not quite worthless, but next to it.
But how many million years would we have to
Well,
wait?
if I were a real estate agent, I try to keep away from that subject. It's a long-term investment, maybe 100 million years, maybe never, because sometimes these things start pulling apart and don't keep going. And sometimes you make your best guess and it turns out that the sea coast will be 100 miles further west. You made a bad guess. I'll say in 50 million years, if this doesn't happen, come and sue me. I'll give you your money back. Now,
Double your money back, right?
the whole point of this is that we are standing in just such a place right now, except this started breaking apart about 180 million years ago. There are several different valleys like this all up and down the East Coast. Gettysburg is in one. This is part of the Culpeper Basin from across in Virginia. The Newark Basin in New Jersey is the same. Connecticut Valley in Massachusetts and Connecticut, and the Bay of Fundy. These are all basins of just this age that started when the Atlantic Ocean started. One of those valleys kept growing. It still is today. It's called the Atlantic Ocean.
What a valley.
It's a big valley, 2 miles deep. That's about the depth of the bottom of the ocean. And you can still see it pulling apart in Iceland. Here, this valley, I don't know just how deep the sediment was in it. I don't know how far down it went. Typically, these go down a mile or two and then is filled with sediment. This has been eroded away, though. There's not much left of it because the land has come back up again and most of the valley fill is gone. This is dinosaur age rock, early dinosaurs. Very few dinosaurs have been found in these basins in eastern United States, but a few skeletons have been. And in at least one place in Connecticut, the state was excavating to put in a new set of state office buildings just south of the state capitol. And they came across a layer of this type of sandstone with thousands of dinosaur footprints in it. Whole families of dinosaurs, because you'd find 2 parallel sets of big tracks and then a whole bunch of little tracks with it, all going together up the rock. They did the right thing in this case, unusual perhaps for state governments. They forthwith ceased construction on the buildings on the site. They didn't start putting the buildings in. Instead, they excavated the layer of rock with all the footprints, put up a geodesic dome, and it's now Dinosaur State Park. And you can go in and see
I've been to.
Yay.
Yeah,
these are not excavated dinosaur footprints that have been carried off and
No,
put
but
into
you
a
could
museum. These are in place exactly where they were found. And you can track the dinosaurs right
You
up
can make your
right
own
up the
dinosaur
slope.
footprint to take away out of, with the cement
You could
stuff.
find the same thing here. I don't know that anyone has found it in this particular unit, but there's an excellent chance that if you keep looking, you'll come across dinosaur footprints in this rock.
Keep looking, Rosie. Maybe you can find a dinosaur
You might.
footprint.
You might even find a dinosaur bone, although that would be highly unlikely. It has been done. People have found them.
But nobody's mining that area anymore for the red stone, where this got quarried.
No, this is not being quarried now, which is a good thing for someone that wants to go dig some out themselves, because active
can come
quarries
back and
generally do not welcome random visitors.
So we could go take a look and see if we see dinosaur footprints.
You could, except that since that quarry has been sitting there for 100 years and nobody's found any in it,
Probably not.
probably not. Now, that's only the beginning of the geology here. That's the first part of the lecture. Second part of the lecture. When the old ocean, Iapetus Ocean, the pre-Atlantic, opened up, it then closed up again. It started closing up 500, 600 million years ago on the other side of the ocean. That's what we saw at our earlier stops. All that activity was on the other side of the ocean. Eventually, like at around 475 million years, it started closing up on this side of the ocean too. And eventually, the two sides collided. And what had been on the other side collided with what was on this side. The same thing is going on today in South Asia. India started off near the South Pole. It started moving north rather rapidly. 40 million years ago, give or take a few months, it collided with Asia. And when it collided with Asia, you got the Himalaya Mountains. Now, when you get a plate collision going on, if it's an oceanic crust, oceanic rock, that's fairly heavy rock, which is why it sits so low, and that's why it's covered with water. And when it collides, it gets pushed back down into the earth. If you've got continental rock, it's both thicker and lighter. and pushing it back down into the interior of the earth is very, very difficult because it's like trying to push a balsa raft down underwater. It just won't stay there. It's too light. It bounces up. So India is continental crust. Asia is continental crust. Neither one would go down.
So you got the
It actually did go down a little bit, but then just slid horizontally, and the Tibetan Plateau is a double thickness, which is why it sits 3 miles high. And the front of the front edge, where it's still colliding, is the Himalaya Mountains. You can't go down, you can't occupy the same space, law of physics. That leaves one possibility, up. And that's why you have the Himalaya Mountains. Same thing happened here when the two sides collided. You ended up with the Appalachian Mountains, which, judging by the Himalayas today, since this was the same process happening, these mountains were probably just as high as the Himalayas. And the Washington, New York, Richmond axis would have been in the 20,000s of feet. And if you stood off to the west, looking in western Maryland, and you looked off to the east, you'd see this line of glacier-capped peaks on the horizon, just as if you were in the Ganges plain today in North India, looking up towards the Himalayas. The rocks in front of the collision zone actually get pushed forward and folded and slid like a rock, like a rug pushing across the floor. Push a rug across the floor, it's going to fold. A part of it's going to slide. That is the ridge and valley province of the Appalachians. It's not the collision zone itself, it's in front of the collision zone. Go further west to western Maryland, to Garrett County, which is the Plateau province. That's now the highest place in Maryland. Backbone Mountains, about 3,500 feet. As mountains go, it's not much. But it's the highest part of Maryland. Same in West Virginia. That's not high mountains, but it's reasonably high, 2/3 of a mile. At the time of the main Appalachian mountain building period, that was flat land close to sea level. However, with all those big mountains to the east, like 5 miles high, that was enough weight that the crust of the earth was actually bent down by the weight, and you had a hole 2 miles deep in front of it. Well, except there was never quite a hole, because as the hole developed, it kept filling with sediment. There is now 2.5 miles of sediment in places like eastern Kentucky, West Virginia, western Maryland.
And that's the place to get coal, right?
That's where you get the coal from.
Right.
Now, where are those 2.5 mile, well, where's the snow from last winter? It's all eroded away. Mountains, in spite of the eternal hills, mountains are not eternal. Give them 50 million years and they'll go away. Same thing happened to the Appalachians. Well, that weight was what pressed the crust down. You take the weight off, bounce it, just like when you get up off a mattress. Sit down in a mattress, the mattress gets bent down. Get up, bounces back up. Except when it bounced back up, you now had a couple of miles of sediment that had been deposited on top of it, and that got lifted up to form the Appalachian Plateaus. So today, what was at sea level during the mountain building period is now the highest part of the Appalachians because of the rebound of the crust. How do we know it was at sea level, by the way?
Well, we see fossils in it.
There are seashells in the rock.
I have some from West Virginia on student trips.
That probably is not the same age. That's probably is older stuff yet. But I worked in eastern Kentucky, and one of the few things I actually discovered in eastern Kentucky associated with the coal beds, which is part of this filling of the basin, I found some cephalopods and brachiopods and corals, and these are all saltwater beasties. And when the glaciers melted at that time, it was an ice age very much like today. the glaciers kept melting and reforming and melting and reforming and melting and reforming. Sea level kept going up and down and up and down and up and down. And every time sea level went up, salt water came in over the coal beds and you got seashells. When the sea level fell again, then it was back to the coal swamps. And this is at the same time that you see those glacier-covered peaks off to the east in Baltimore and Washington, which now, of course, is down to sea level. Okay, any questions? Oh, no, and I forgot, I almost didn't mention the one thing that's making me talk about it here. And that's because the line of separation or of connection between the African rocks and the North American rocks, that's called a suture, by the way, by modern geologists. That word did not exist in a geological context when I studied geology because plate tectonics did not exist then.
Oh, wow.
However, today it does. And that connection between two separate plates that started out far apart from each other and now are joined together, that's called a suture. It comes from medicine.
Yeah.
And that suture runs right through here, right about where we're standing.
So
You
does-
don't get to see it here because the later pulling apart and that sediment that was deposited in the basin covers it up.
So if we dug deep enough, we'd find seashells?
Well, probably not because the underlying rock here is heavily metamorphosed
Oh, okay.
That would crush him.
Yeah, okay, fair enough.
and
Yeah, that won't happen again.
but it could have had seashells at one time.
One time.
The trouble is I don't know exactly which side of the suture we're on. And if it's the rock on the eastern side of the suture is our old friend the Mather Gorge. And it's pre-seashell.
Got it. Right.
Pre-shell. Nobody had invented shells yet. The rocks on this side could conceivably have seashells, except that it is metamorphic rock, and that tends to destroy the fossils.
Got it.
But it could have them. If you want to see good seashells, well, aside from Calvert Cliffs, which is just 12 million years old, that's hardly worth looking
And the
at, just the
ocean.
other day. And you go out to Sidling Hill, take the exit just this side of Sidling Hill. There's a quarry there with some seashells about 350 million years old. So you can get to see seashells that are way inland from the time when the ocean flooded up over the continent. Okay, I would very much like to show you the suture zone, and one of these days I'm going to get really ambitious.
We'll figure it out.
No, but it's mapped.
Oh, okay.
It is mapped. You can get the geologic map of this area, and they map that suture as leaving the valley a few miles north of here and heading northeast up towards Rockville. And all I've got to do is go out and take my car on some weekend, and because it's mapped, that means the geologist who did the mapping found evidence of that suture zone,
Right.
and so was able to put it on the map. If I can just find the places that he used to make the map, then I can find the suture. Which is, I guess, I've read the description of it. It's a zone of milonite, which is a word you now know, about half a mile wide, in which the rock has been completely ground up in that fault zone. It's actually been given a formation name. It's a wide enough piece of rock. It's called the Pleasant Grove Formation, also known as the Pleasant Grove Thrust Fault. Okay, any questions?
So this was like was this like a riverbed down here or something?
Oh yeah, at the time,
Is this a mill where they had water
a
going
mill.
through?
Oh,
Was it water?
right
Running
here,
mill.
this
That was the
was where
water.
they ran the water, running water, to run the mill. That was, running water was the power source.
And the water would have pushed the
Over
wheel, and the
there,
wheel would have
probably.
pushed whatever machinery.
Yeah,
they were
the
using.
water
would've-
wheel gets run by the running water, and then that works the grinding. This is
Cut the zone.
this is before there was electricity to do this sort of thing with.
Before gasoline.
Yes,
If you had a factory, you wanted to be by a river so you could use the river
you
power.
use water
your
power to do
machines.
it. Okay, I do have another thing to show you here. We'll continue down that way, and the best way to do that is to come back out here. Okay, now, what I wanted to show you here was this black rock, which is not in place but is local. This is found around here.
It's not basalt, is it?
It is basalt. Well, it's actually a little bit too coarse-grained to be
be
true basalt.
Okay.
Geologists have given it a name,
Well, tell me what they
diabase,
should
which is in between gabbro, coarse grain, and basalt, fine grain.
over here.
If you called it basalt, I'd be perfectly happy. But you can see a little bit of sparkle in it. And the fact that you can see the sparkle means the grain size is a little bit too big to truly be called basalt. That's the pyroxene and the calcium plagioclase, which both have good cleavages, that's giving you the sparkle. Now, when you pull apart the continental crust, you lower the pressure because you're taking away some of the weight that was sitting on top. And you're making a crack that goes down. And when you do that, the hot mantle rising underneath, and it's the hot mantle rising causing a convection current that's causing it to pull apart. That actually is going to start giving you partial melting, and if you partially melt mantle rock, you get basalt magma, which then works its way up in the cracks and ends up as basalt dikes, or diabase dikes, diabase being the name they give this coarse basalt. And there are mapped through this area diabase dikes running across the country here that date back to the same time as the red sediments here, which were forming, again, where it was pulling apart. And you can get an independent date on the sediments and the dikes. The sediments you do with fossils, although you don't find seashells in here and damn few dinosaur pieces. They do find things like pollen in the rocks that can be dated, plant fragments that you can use to date it. And in the basalt, you can use radiometric dating. There's no zircon in it, but there are other radioactive radiometric methods that you can use. And you can check that the dates are the same. The fossils give you the date for the sedimentary rock, and the radiometry gives you the date for the igneous rocks. Now, in some places, such as Connecticut, you don't even have to do that to compare, because there will be actual basalt lava flows that came out onto the sandstone and then were covered by sandstone. So you can tell that the sandstone and the basalt were laid down at just about the same time. And that's commonly the case. It's very likely that thousands upon thousands of square miles of eastern North America were covered by basalt, but the only place it's preserved is in these valleys that have dropped down. It's only a good guess that those areas that aren't in the valleys had basalt too. We really can't tell. It's the same in New Hampshire, by the way, in that in late Mesozoic time there was some tremendous volcanic eruptions there. The volcanoes are very much like Yellowstone today. And they believe that much of that part of the world, most of New Hampshire, was covered by lava and tuff volcanic ash. But the only place it's been preserved is in the calderas, the places where the crust has collapsed and preserved that lava and tuff that was dropped down into the hole. Otherwise you don't get to see it, because the whole area has been eroded down a couple of miles, and anything that on the top is gone. It's eroded away. Okay, that's all I wanted to say here. Are there any questions? Okay, let's go on. We have one more short stop, and then we go have lunch. Food, yes.